Hello, this is Aishwarya Radhakrishnan, and my project title is going to be Deformation and Material Performance. So, what is stress, strain, and factor of safety? Stress is the applied load or force divided by the cross-sectional area of the material. Stress is defined by force divided by area. Strain is the amount of material that deforms per unit length. Strain is defined by the change in length divided by the initial length. Factor of safety is the ratio of material's load-bearing capabilities to the actual load it experiences under operating conditions. Factor of safety is yield stress divided by working stress. Plastic deformation. It usually occurs to the breaking of bonds with original atom neighbors and reforming bonds with new neighbors. After removal of stress, atoms have relocated and do not return to the original position, which differs from elastic deformation. So this is how the atoms are initially arranged. Once the load is applied, this is how the deformation occurs, and the atoms break bonds with their initial neighbors and they reform new bonds. Once the load is removed, the atoms do not return to the original position and it deforms and changes from its initial position. This is different in elastic deformation, where after the load is removed, the atoms go back to its original position. Um, what is the role of factor of safety in design and reliability? Design assurance. Factor of safety ensures structures can handle loads beyond normal, accounting for uncertainties in material properties and external conditions. Risk mitigation. It reduces the risk of catastrophic failures, enhancing structural safety and protecting against unexpected events like weather or accidents. Plastic deformation. For materials like metal, it prevents permanent deformation by keeping stresses below the yield point. Reliability enhancements. By incorporating a margin of safety, structures become more reliable, durable, and able to withstand long-term services without compromising safety. Load and its impact on materials. Stress generation. Applied loads create internal forces within a material, leading to stress, which is force per unit area. Plastic deformation. Applied stress may lead to permanent plastic deformation in metals. This occurs when stress exceeds the yield strength, causing atomic level changes and irreversible strain in the material. Strain behavior. Strain, which is the measure of deformation, increases with applied stress. In plastic deformation, the material undergoes strain without fully returning to its original shape, leading to changes in dimension or shape. Necking and fracture. In some cases, especially under high stress, localized necking may occur where the material undergoes severe deformation at a specific point before ultimate fracture. This is the stress-strain relationship of a material. So this is the linear part where the material is retained in its original position. The slope can be defined as the Young's modulus slope or the elastic modulus slope, and this is the elastic region, and this would be the plastic region. This is the fracture point, and this would be the tensile strength point, which is the highest yield strength that a material can acquire. So overall, this is the relationship between stress and strain of a material. What is the importance of stress, strain, and factor of safety in assessing material performance and structural integrity? Stress. Stress measures internal resistance to external forces, which is crucial for evaluating material responses to loads. Strain. Strain indicates material deformation under stress, aiding in assessing an elastic and plastic behaviors. Factor of safety. It determines the margin of safety between expected and failure-inducing stresses, ensuring structural reliability. These concepts are vital for designing safe and durable structures across engineering disciplines, ensuring performance and integrity. So for this project, I did a 3D model in SolidWorks where I modeled a rectangular beam with a load of 400 newtons applied at this specific point. By applying the load of 400 newtons at this point, the stress, strain, deformation, and factor of safety was analyzed for two different materials, steel and aluminum. So properties and uses. Steel, with respect to aluminum, has higher yield strength, toughness, and is slightly resistive to corrosion not really compared to aluminum, but however, it can be resistant to corrosion when it's stainless steel. But steel makes it ideal for construction, automotive, machinery, and infrastructure projects. The uses of steel may be in buildings, bridges, pipelines, and heavy machineries. Aluminum has lower yield strength when compared to steel. It is flexible, lightweight, corrosion resistant, and has excellent thermal and electrical conductivities. The uses of aluminum may be in aircraft fuselages, automotive parts, electronic housings, and beverage cans. Based on the model done in SolidWorks, this is the stress distribution for steel and aluminum. So steel has lower stress distribution across the body when compared to aluminum, which has higher stress distribution across the body. This was determined by the ranges provided in the model. So the range for the stress distribution in aluminum is higher compared to the range of stress distribution in steel, which is lower. So the strain distribution in steel is lower compared to the strain distribution in aluminum, which was higher. This is also determined by the range and the starting point where the strain distribution occurs. The stress concentration. The stress concentration for steel is higher where the load is applied. So the stress concentration was determined by the area where the load is applied. The stress concentration for steel is higher and the stress concentration for aluminum is lower. This may be the reason why the stress distribution for steel was lower and the stress distribution for aluminum was higher. Considering the factor of safety, the factor of safety for steel is higher than the factor of safety for aluminum. So based on the results, steel had higher stress concentration where the load was applied, however, lower stress distribution, while aluminum had lower stress distribution and higher stress distribution. Aluminum had lower stress concentration while higher stress distribution. With respect to strain, steel had lower strain while aluminum had higher strain. With respect to factor of safety, steel had higher factor of safety while aluminum had lower factor of safety. Considering stress and strain, steel showed higher stress concentration at the load application point, but lower overall stress distribution across the body, indicating it's less prone to deformation under the same loading condition compared to aluminum. Steel showed lower strain since steel has higher modulus of elasticity, causing the material to be stiff and prone to lesser deformation. Aluminum exhibited lower stress concentration at the load application, but a higher overall stress distribution, meaning the material underwent more deformation evenly across the part. This could imply a more efficient material usage where the load is more evenly distributed. Aluminum further showed higher strain due to lower modulus of elasticity, causing the material to be more flexible and prone to deformation. Factor of safety consideration. A higher factor of safety for steel may reflect its inherent strength and stiffness properties, allowing for a more robust design that can handle heavier loads or more severe conditions. Steel's higher factor of safety may indicate a higher level of reliability and durability in the given application. With steel having a higher factor of safety than aluminum, it suggests that the design requirements or safety standards for the application demand a greater margin of safety, possibly due to higher expected load, criticality of the structure, or safety regulation. If weight is a critical factor, then aluminum part might be more suitable despite its lower factor of safety. If the load carrying capacity is the priority, weight is less of an issue, then steel might be the preferred material. So the suitability based on the 3D model structure or the case study that I did. So steel provided greater structural integrity and is more suitable for heavy load applications, an environment where stiffness and durability are critical. Aluminum offers advantages in lightweight constructions and is and in application where resistance to corrosion and ease of maintenance are required, since the material is flexible and less stiff. Thank you. And this is the 3D model that I modeled in the SolidWorks. That's all I have for today. Thank you so much.